Hi everyone! So in this video we're going to go ahead and talk about something called thermochemistry calculations. We learn about specific heat and also things called insulators and conductors. So let's go ahead and get started. So first of all, I want you to go ahead and think about this situation. You have two different spoons that you're using to stir some soup on the stove. So you have a wooden spoon and a metal spoon. And you get distracted and you leave them in the hot soup for a little while. And then you come back. Which spoon is going to be hotter, the wooden spoon or the metal spoon? So go ahead, pause the video, write down your answer, and then we'll talk about it. Okay, so you probably said that the metal spoon is the one that's going to heat up faster. If you leave it in that hot soup too long, it's going to be extremely hot. You might even burn yourself if you're not careful. Versus the wooden spoon, you can leave that in there pretty much forever, and it's not going to get too hot to touch. That is because these two materials, wood versus metal, have different specific heats. Okay, so specific heat is the amount of energy needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. Now, one thing I do want to point out here, remember 1 degree Celsius is equal to the amount of change for 1 Kelvin, so we can actually use those interchangeably for this unit. So we can use Celsius. So units for specific heat are usually given in joules per gram per degree Celsius or joules per gram per Kelvin. Remember, we don't use degrees with Kelvin. So we can just go ahead and use both of those easily. And the specific heat varies based upon the identity of the material. So water actually has one of the highest specific heats. It is 4.184 joules per gram degree Celsius, which is why it takes a long time for water to heat up. Okay, if you have that pot of water on your stove, the metal is going to be hot from your pot, but the water is still going to be cold. It's not going to be boiling yet. That's because water has such a high specific heat. We also see this idea with water outside. So if you try and jump in a swimming pool in early May, it might be 80 degrees outside, but that pool water is still going to be cold unless you have a heater. But going into the winter time, or as we start to cool down in the fall, that water in the pool is going to stay warmer longer than the rest of the air temperature. Some other examples we have of specific heat are aluminum and gold, which are much, much, much lower values, as you see. Specifically, gold has a really low specific heat of 0.129 joules per gram degree Celsius, meaning it's going to take less energy to heat up that gold. Okay, so this also plays into the idea of insulators and conductors. You've probably heard these terms before, but we're making it a little bit more specific. So an insulator is something that resists the flow of energy, and that can be heat, electricity, or sound. And specifically in this unit, we're going to think about heat because we're thinking about thermochemistry. So insulators are things that have high specific heats, meaning it takes a lot of energy in order to change their temperature. So some examples of this are air, rubber, wood, and polystyrene foam. Okay, so air is actually a really great insulator. We don't think about it a whole lot, but if we can trap the air so it's not moving around, it's actually going to keep things at same temperature and be resistant to changing. In contrast, we have conductors. So these are something that allow energy to easily flow through that material. And they tend to have low specific heats, meaning a small amount of energy will change their temperature. So some examples of this are graphite, like what you use in your pencil leads. Most metals, so copper and aluminum, all those other ones, they tend to be conductors. There is actually an equation we can use to calculate the specific heat of a material, and it is shown there. So Cp, which stands for the specific heat at a given pressure, is equal to Q, which is the amount of energy either lost or gained by the system. M is the mass of the sample, and delta T stands for the change in temperature. And you probably saw that triangle back in math class when you were doing slope. You'd have the change in y over the change in x. Well, here, same idea. Change meaning the final minus initial. We can actually go ahead and rearrange that equation to find the amount of energy that's being either released or absorbed. So Q is equal to M times C times delta T. And we're going to be using that equation a lot in this unit. Let's go ahead and try this out with some examples. Okay, so let's go ahead and try this out with some examples. So a 4.0 gram sample of glass. Okay, so let's go ahead and try this out with some examples. A 4.0 gram sample of glass was heated from 274 Kelvin to 314 Kelvin, an increase of 40 decimal point Kelvin, and was found to have absorbed 32 joules of energy as heat, what is the specific heat of this type of glass? So I already have the equation written down. We want to use the one where specific heat is equal to Q over M times delta T. And let's go ahead and read through the equation and identify our variables. So a 4.0 gram sample. So that is going to be our mass for this problem. And we're told it was heated from 274 to 314 Kelvin. And this question's really nice that it tells us the difference between those numbers. So that is going to be my delta T. If I wasn't given this information, I would need to take the final value, which is 314, and subtract out the initial value, which is 274. So they saved us a step. And was found to have absorbed 32 joules of energy. So that is our Q. Okay, and then we're being asked to find the specific heat. So that is going to be our CP. Okay, so once we have all these variables identified, let's go ahead and actually plug them into our equation. So Q, Q, the amount of energy, is 32 joules. That goes on top. M is the mass of our sample, which is 4.0 grams. And then our delta T is the 40 with the decimal point Kelvin. That is important for sig figs. Okay. And then we want to go ahead and then solve for that value. So 32 divided by the product of 4 times 40. Okay, so that gives me a value of 0.2 joules per gram Kelvin. So I'm just taking the units here to get my units for my specific heat. But we do need to think about sig figs. So in the case of all of these numbers, they have 2 sig figs, meaning my answer also needs 2 sig figs. So here, remember leading zeros never count. I need to add a 0 in order to get to that same number of sig figs. So the answer for this question is 0.20 joules per gram Kelvin. Okay, so let's go ahead and do the second part of this question. It asks, how much energy will the same glass sample, so same glass sample, meaning that it has the same mass, so 4.0 grams, and it has that specific heat we just found, so 0.20 joules per gram Kelvin. Okay, so how much energy will the same glass sample gain when it's heated from 314 Kelvin to 344 Kelvin? So in this case, I have different temperature values. So let's go ahead and start to plug in this information. So Q is the amount of energy. That's what I'm being asked to find. M, that's the same as before, so that's going to be 4.0 grams. My specific heat, I calculated previously, so 0.20 joules per gram Kelvin. And then I want to find my delta T. Remember, delta T is the final temperature minus the initial temperature. So my final temperature is 344 Kelvin, and I'm going to subtract from that 314 Kelvin. So I go ahead and actually find that value. That is a difference of 30 with the decimal point Kelvin. Okay. So now I have these 3 values. I'm going to multiply them together to get my answer. So 4 times 0.2 times 30. So that gives me a Q of 24. And now I need to think about my units. Okay, so my grams, those are canceling out because I have 1 on top and then 1 in the denominator. My temperature cancels out as well because I have Kelvin on top and then Kelvin in the denominator. So that leaves me with a unit of joules for energy, which makes sense because joules is a unit of energy. And if I double check my sig figs really quick, all of these numbers have at least 2 sig figs. So that is why I have it rounded to 2 sig figs as well.